Hello. We've previously talked about diodes, including mentioned their specific types, ratings, and models, but in this video, we'll be covering them in further detail. Okay, let's start with a little refresher on diodes. In the classic sense, they act as a one-way street. Current can only flow in one direction. But in practice, they have a forward and reverse bias. The one-way street is forward bias, while blocked to a point in reverse bias. There's a minimum threshold voltage, the forward voltage, that must be achieved for it to even start to flow in forward bias. This is usually somewhere between 0.3 and 0.7 volts, often depending on the material. However, reverse bias only tolerates voltage to a certain point. That threshold is known as breakdown voltage, which can cause a sudden current flow, which may damage the component or even the entire circuit. If it goes too long, then it goes into avalanche effect, where the voltage suddenly multiplies to dangerous levels. Now, there's many types of diodes, and some of these types can apply to the same diode. We've got rectifier diodes, LEDs, Zeners, tunnels, varactors, diacs, triacs, SCRs, photodiodes, switching, fast recovery, Schottky, transient voltage, thyristors, avalanche, pens, lasers, step recoveries, among potentially others. All right, let's see what our options are in every circuit here. First, we have an LED. I only have it at 1 volt. So let's keep turning it on until we get to a certain point where you can actually see it glow. I don't have a resistor hooked up to this because I'm just changing the voltage. All right, actually, oh no, okay, so it actually does flat out need 2 volts to light up. All right, okay, we'll just put it on 2 volts. And it's getting like 20 milliamps. So it's got the perfect setup right here. And that's because of how simple it is. You can adjust a few things. So the next one is just a regular diode. The only thing you can really adjust, saturation current, ohmic resistance, a few things, but you can't really set it up for a proper breakdown and avalanche, no matter what you do. Um, and then we'll reverse it. Well, actually, you know what? Let's just start by seeing how it works. And not even sure there's a threshold voltage, to be honest. Well, let's put it to 0.1, see what happens. Okay, there's no flow. All right, so 2.3, 4. So not a geranium diode. 6. Oh, now we're starting to get something. Oh, let's go back at 5. Oh, no, we were kind of getting something at 5. I mean, insignificant at this point. So where's it starting? 3. Pretty sure I didn't see anything on 2. Okay, so nothing at 2. So it's actually starting at 0.3, but it's still insignificant. It's picoamps. So we'll bring it up to a 7. Okay, microamps, 8. Starting to see the animation. So about there is where we're getting some actual milliamps. Um, let's reverse this. Let's bring it up. I don't know what the breakdown voltage would be, but let's just say, I mean, we're getting into the kilovolts and nothing's happening. Not saying any numbers. Oh, wait, whoops. Try this again. Um, yeah, it's just not working over a certain, well, it's not working because it's in reverse. But yeah, even at the higher, this should be an completely, utterly out of control number. All right, well, then let's look at a Zener. Um, started at, you know what, let's go all the way down to 0.1. Okay, nothing, 0.2, 0.3. All right, we're starting to see something there. Now let's just turn it up to 1 volt. Okay, and a lot of amps here, so you know, resistor would be nice. So it gives us, we actually have a breakdown voltage number here because otherwise it wouldn't work as a Zener. All right, let's reverse it and see what happens. Nothing. Okay. Two, or actually, wait, try this. 10, actually at 10 volts, it should be, huh, 20. Oh, wait, because I'm looking at the wrong, wow, I'm smart. I'm looking at the wrong thing. I've actually got to increase it. So let's increase it to 5 volts. Nope, nothing. 9, nothing. And then 10 is where we have a flow. 20, we've got even bit bigger flow, probably more than we actually want. Um, Once we get past, it's meant to mess around in a particular breakdown voltage. If you go higher than that, you run into the same avalanche problem. But that's what you can do with every circuit. All right, let's see what our options are in Falstad. Passive components, do we have anything? Nope. Okay. Put active components. We've got regular diode. We've got, well, okay, we've got LED. It's over here. Actually, it's meant to the symbol. No, okay. But we can actually pick specific things for the LED, including technically making our own model. We've got Zeners. Let's see, what else do we have? Oh, SCRs, Diac, Triac, let's see, Veroact, Verocap, tunnel diodes, triads, but in this case it's a vacuum tube. So yeah, we've got a lot of options. We have a pretty classic diode here. Start off. I think this is about the operating. Not entirely sure. So let's set a, where's the slider option? Oh, because it's already on. So we can take it down and we'll notice. Actually, let's do one even better. Let's put on a model, a general purpose one, so we can see how something might work a little bit differently. Actually, I got an idea. Let's set a minimum of 50, a maximum, I guess, I don't know, we'll do 50, whatever, it doesn't matter. Um, so let's start it off at 0. So we have nothing. 1, we've got flow. Let's see within that what we have. For some reason, the slider menu isn't coming up. But let me see if that's just a problem with the diodes in general. No, yeah, weird. I don't see the. Hmm. So I'm not entirely sure what turns it on or off. Oh, wow. No, I'm thinking of the wrong. Not looking at the diode. I'm looking at the voltage source. All right. Need some fixes to the voltage source here. So at 0, nothing. Oh, it's just going to jump it to 1. So it's weird. Yeah, I have set the step to At 1 volt, it's definitely flowing. Let's actually set it to, I don't know, 0.1, see what happens. The flow's there, but it's negligible, and it's just gonna keep going there. All right. Actually, let me just change the slider temporarily. Do it to 0 to 1. Okay, so we're getting a little bit, but it's nano, and it keeps going up. Question is, what do we consider on? So yeah, 0.7. We're starting to see that. And it's climbing pretty quickly, actually. Mind you, yeah, there's no resistors there. So we get to 1 volt, and we've got 1.8 amps. I think with the, yeah, this would probably be over spec of what it should be. So let's look at some different numbers here. Let's set the sliders to 50 and negative 50. We'll set up 1. All right, let's keep increasing it. It'll just go crazy in amps. Again, this is way over spec, obviously. Everything would blow up at this voltage range. But yeah, you get the idea. Let's bring it down, back down to, oops, down to 0. Whoops, this button is slippery. All right, doing reverse. At negative voltage, and you'll know that it's not going up, so it is doing its job. It's blocking in the reverse bias. But up to what point? Now we have the numbers, but we're going to ignore those for the moment. Okay, now let's change that slider again. Let's make this negative 50, say negative 100. Increasing it, still blocking. Let's take it to 200. Hit the wrong button there. You know what? I'll just see what happens when we do 200. Oh, just real. Yeah. Hmm. Okay, now we're getting it. Let's see, 200's not cutting it. Let's do 200, 300. Okay, still nothing. This has got to be some pretty hence model. It could just be the problem with the behavior. Oh, suddenly got a jump at negative 400. How does it really go up that much? Interesting. So now we're finally getting flow from the reverse. So we're hitting our breakdown effect. Now another way to look at this is with current voltage. Um, and we'll see where it finally, in forward bias, where it finally reaches a point where the current can flow. And then it goes out the other end. I'm not sure why it's not dipping down here, or if you can even show that in Falstad. But yeah, as the voltage eventually is supposed to reach a breakdown point here. Actually, the problem may be the model. Let's switch it to the general purpose model, see what we get. Okay. What about, we'll change max voltage. See what happened. We know that at 400 it started to break down. see. Let's reset. All right, let's do 500. Ah, there we go. We actually see the breakdown for some reason with this model isn't starting to kick in until negative 400, which sounds wrong for this diode model. I should really look it up. But this is the kind of curve. You've got the forward. Now we've made such a distance that we can't really easily see that. Um, but we'll change it back. We'll do 10. Let's reset that. And what did I just mess up? Probably my scaling. Okay, there we go. So we see that it's starting to really kick in around, I guess, 2 volts here, somewhere in that vicinity. And then it's still being blocked until it, for some reason, gets out to 400. So let's set this back to 5. Now, yeah, you'll see kind of over here past 400, it goes into breakdown and avalanche. Now let's start with the rectifier diode. This is often what I call a classic diode in that its function is to act like a one-way street even when handling fairly high current loads. The most common type of diode in hobby kits, you'll probably get a 1N4000 series, which goes from 1 to 7, and these are considered general purpose rectifier diodes. The O1 can handle 50 volts, and then as you go up, they can handle more. Keep in mind this entire series is only set to work with 1 amp or under, and things known as power diodes are used for when you need more current than that. They're called rectifier diodes because their original main purpose is to rectify AC to DC, but kind of at the hobby electronics level, you could just use them as a general purpose diode, or I've coined the term classic diode. Let's take a look at a regular old general purpose diode here in QSpice. So we have it taking a sweep from negative 100 to 100 because I want to show you the full breadth of this. We got a basic model down here. All right, as you can see from this IV plot here, we've got a section where it's completely flat, no current whatsoever until we get to, let's see, about 1.12 volts, somewhere then it starts to climb. I don't really have too much of a resistor on, so the current gets obviously higher and higher than the uh, real diode would be able to handle. The opposite end, we eventually get to negative 50 volts, and we've got our reverse bias volts, so at 50 it starts to break down. And then we have the switching diode. This is designed for rapid switching on and off, used for signals and logic as opposed to being designed to handle higher voltages. It allows for a pretty fast recovery between the on and off states. The 1N4148 is a common model for hobbyists. In fact, you may even find this in hobby kits. It uses very low voltage control, and it's really meant for logic signals. They can usually handle much lower current, usually in the hundreds of milliamps, but it can handle switching times literally measured in nanoseconds instead of the microseconds with most diodes. Then we have step recovery diodes. These are similar to fast recovery ones, but they store a little bit of a charge, which allows them to continue forward conduction and then just quickly shuts it off. It'll drop off even more quickly than fast recovery. This is used a lot with RF, microwave, signal generation, usually in the mega, if not gigahertz. And then, as I just mentioned, there's also fast recovery diodes. They're meant to turn off more quickly than a classic diode, and they kind of occupy a middle ground between rectifiers and switching diodes. They can handle high power similar to rectifier diodes, but with a higher frequency, kind of similar to switching diodes. There's a couple of models, usually the FR107 and 2R7 are commonly available for hobbyists. One handles 1 amp, the other can handle 2. Now we're going to compare three diodes. We've got our regular rectifier diode is 1. We've got our switching diode is 2, and then we've got our fast recovery diode as 3. All right, so let's actually take a look at the plot. Well, 1 is our regular rectifying diode. It's got a pretty big recovery time here. And then 3 is our fast recovery diode, so a lot faster. And then we've got a switching diode, which just looks like a straight line until we zoom in a little bit more. And it's even smaller, a fraction of the size of the fast recovery. um, Now, keep in mind, switching diode, it's meant for signals and logic, whereas fast recovery and regular diode can obviously handle a lot more, but it's especially made for very low voltage signals. And it can only handle much lower current, I think in the maybe the hundreds of milliamps. It really depends the model, but the switching time is like a couple of nanoseconds as opposed to a couple of hundred nanoseconds for a fast recovery or microseconds for a rectifier. All right, let's look at a step recovery diode. Now, I'm going to preface this by saying that the model is not perfectly accurate, that it actually takes a lot of work to really show what a step recovery diode can do in SPICE, but I have a very basic model here to just kind of take a look at. So first, we're going to just hook it up. It's an MA144769. I'm going to say that I've never worked with recovery diodes directly in real life. All right, taking a look at the result here, we see an extremely small recovery. Now keep in mind, this entire scale is just 1 microsecond, so it's not even a tenth of a microsecond. And a tenth of a microsecond would be 100 nanoseconds. So this is, I don't know, maybe like 2 nanoseconds or so. All right, let's go back to our comparison, which is getting increasingly crowded here. We've got our regular rectifier diode on 1. We've got our switching diode on 2. We've got our fast recovery diode on 3. And we've got our new step recovery diode on 4. All right, let's take a look here. So as I said, 1 was the regular rectifier. Okay, big recovery time. Uh, 2 was, I believe, this switching. 3, I don't know, wait, yeah, hold on. Yeah, 2 was switching, 3 was fast recovery, and 4 is our new step recovery. Now let's take a look at one little thing. If I'm not mistaken, this sort of illustrates the snap recovery, at least in some point here. Let's take another look here. Then we have Zener diodes. They'll operate pretty much like a typical diode in forward bias, but they're designed to actually operate safely right in that junction at breakdown voltages and reverse bias. This allows for voltage control through through the diode at breakdown voltages, even when the current can wildly vary. The Zener effect is quantum tunneling, where electrons, in a seeming violation of Newtonian physics, can push through material by tunneling because of a strong electric field. This occurs usually at a lower breakdown voltage than you might see with other diodes, um, and then past that is the obvious avalanche breakdown. There's a number of subtypes too. You can have low powered Zeners for like signals, power ones for higher voltages, precision for referencing when you need a really precise voltage, or even temperature controlled ones for low drift. If you're going to see any, you're going to see the 1N47 100 family 33As or 44As. These are low powered. They're meant for logic signals for the most part. All right, and this with Falstad here. This is a IV curve. Now in forward bias, it works basically like a regular diode, but so let's just take a look. It's, I don't know, around 1 volt. It starts to go up. Sounds about right. It's going into the thousands of volts, but lack of resistors and all that. Um, and then it hits breakdown really early compared to the regular diodes, but that's the point. Around, I don't know, 5.8 or so. All right, let's go into QSpice and look at a Zener diode. We've defined the model up here. Just pretend you can't see everything that's on the model. It's a rough estimation of a very classic Zener diode. Um, so let's see what this looks like. And we're going to go between -10 and 10 volts. Now keep in mind that Zeners are meant to work with reverse biases. Um, Doing it forward, I mean, it would still function like a classical diode, but that's not the point. So we have this reversed. So let's run it. All right, and here's what we got. We've got a whole lot of nothing in the middle until it gets to 3.3 volts. And then we've also got where it starts to function forward as well. So you'll notice once it gets to about 3.3 volts in the reverse, it just completely drops off. It's almost a straight line, and this is how a Zener diode would look. Then we have tunnel diodes. Technically, this means any diode that uses the quantum tunneling effect that we just described. Now, tunneling at low voltage, the current increases quickly. At medium, it drops, the tunneling lessens, and then at high voltage, it kind of behaves like a classic diode. Negative resistance, the voltage increases, the current decreases, and so on. Very fast because of the tunneling effect, as opposed to storing charge. Now, the tunneling effect can exist in many types of diodes, but there are diodes that were built specifically for the tunneling effect, especially when they were new. You're not going to really find those much anymore because they've been incorporated into other types, and there's subtypes such as Zeners now. You might find some vintage models that are sold to replace really old components. I'm talking like 60s, maybe 70s stuff. Then we have avalanche diodes. Now, I've told you about how a classic diode, if you put too much current in reverse bias, then it enters an avalanche state electrons collide with atoms, causes current multiplication, which can destroy the diode. An avalanche diode is meant to handle an avalanche state relatively briefly without any damage to the diodes. So it's made to handle certain high energy surges on the reverse diodes. Transient voltage diodes operate as avalanche diodes for the purposes of surge protection, for example. Then we have the PIN diode. This means there's p-type and n-type material in the diode, but in this case, there's also an intrinsic layer in the middle, which is an undoped layer. At low frequencies, like DC or signals, it works basically like a classic diode, but at high frequencies, it stores a charge in that intrinsic layer and allows the resistance and reverse bias to be controlled, kind of like a variable resistor in a way. Certain diodes might employ PIN for surge protection, power regulation, attenuation. And then we have a Voractor diode. Sometimes it's called a Varocap diode. It basically functions like a voltage controlled capacitor. The depletion region, it stores a charge. When you change the voltage, you change the depletion region. It operates only in reverse BIOS though, so it's used for tuning RF circuits, voltage control oscillators. These were constantly used at radios and early TVs for channel tuning. Again, you can use them in hobby electronics, usually for tuning, maybe DIY radios. The BB 910 model. It's used for VHF tuning. The 1SV 149 used for AM radio tuning and some low voltage oscillators. Then we come to thyristors, and they're really a whole category of triodes, although some people won't use the word triodes unless they're referring to a three-terminal vacuum tube. So they're not technically diodes, but they include SCRs, triacs, and I guess diacs in a way. It's a little confusing. But again, they're not technically diodes because they have three terminals, so they have a gate control in the middle. Thyristor is designed in some cases, you need a relatively small pulse to turn something on, and it often remains on even if that signal is removed, unlike a transistor. Some thyristors may change up this behavior a little bit though. Then we come into a diac. Well, this is just a diode for alternating current. It's made to handle both the positive and the negative voltage of AC. Um, Sometimes it's grouped with triacs and such, but it is technically a diode because it has two terminals. Um, Voltage is first applied, it blocks current, it reaches a threshold. Notice the breakover current, it suddenly turns on and it lets current flow at that point. The voltage drops, and once it gets down below a certain threshold, it turns off. This is an important behavior. It can create a really clean triggering pulse for a triac. The two are usually combined. Um, and it can be used for light dimmers, fan speed controls, heater controls, AC power regulation circuits. The DB3 model seems to be really popular for at least triggering triacs because it's very cheap, used by hobbyists. All right, here we're in Falstad, and I'm just doing a diac by itself. So how does the diac work? Well, it's for AC, so it goes back and forth. It has a basic breakdown voltage. And in this case, here we go. We're just slightly over the breakdown voltage. Now what happens when we take it down? Eventually stops until you take it back down. Let me reset this again. This point, since it already hit the threshold, it's going to stay that way. Go back up the other end, and we'll bring it down. It'll vary until it gets back to zero. Then once it takes back to zero, you're going to have to hit the breakdown voltage again to turn it on. That's very important. Now, here's a quick little basic diac model. Bit defined up here, and I'm doing a sweep. Here you go. It's not as interesting to look at since I can't just take the slider back and forth to show you, but you see the numbers for the basic breakdown here, which is 30 volts. You can see what the current does. I have no resistors, so obviously the current is really high for a diac. Next we have triacs. They're usually lumped in with diodes, although they are not technically a diode. But a triode is for alternating current. Um, it's a type of thyristor, I guess, technically. It conducts current in both directions. It can be turned on by a small control pulse, usually fed with a diac, but it doesn't have to. This makes it useful for AC as it can conduct both the positive and negative voltages. The BT136600E is a model for general purpose motor control and switching. All right, here's a triac, which usually often a diac is used as the triggering pulse, but yeah, we've got power going through here. Let's turn off the power. Okay, we're back down to nothing. Let's switch it on, switch it off. It doesn't go off until the current's on, and that's pretty simple. That's a basic idea of a triac right there. Next, we have the silicon controlled rectifier, or SCR. This is another one that's not technically a diode. It's a type of thyristor, similar to a triac, but the switch stays on in the absence of gate signal, unlike others which turn off. This one only turns off when the current drops to zero, so what it's conducting. This is a very important feature of it. It's used for controlled rectification, power control, motor control, and sometimes even for light dimming. Um, there is a model of what I just described, which is the SCR version of the triac model. All right, here we have a silicon controlled rectifier. We're going to start the current that's going through it from anode to cathode. We're going to turn on the switch to turn it off. Now we're going to turn off the switch and the current is still flowing. Turn it on, turn it off. So 344 millivolts, turn it off. It's the same. Even though the animation's speeding up, I believe that's voltage. Or wait a minute. Okay, so yeah, Kate. All right, that's why the animation changes. But yeah, doesn't matter with the switch here. You have to turn it, we have to kill the current to actually kill it. We turn it back on. There we go. And then we have the photodiode. It basically senses light. The protons knock loose electrons, allowing for more current to flow, more light equal more current. It operates in reverse bias, meaning that current flows from cathode to anode. It has a classic PN junction diode, but its subtypes can include PIN, which is faster and more sensitive. You've got avalanche ones that have very high sensitivity and internal gain. This can kind of be thought of as a reverse of photoresistors in that resistors restrict current with more light, while diodes increase it with more light. The BPW32 model that's used for photo interrupters, IR remote controls, control and drive circuits, etc. All right, here's a little circuit with a photodiode in QSpice. There's not too much to show, except that basically we have a little current source over here that basically acts as our light, and we're just going to be taking it from 100 microamps to 1 microamp. Now, I believe the way I have this set up, 1 would be dark, 100 would be fully lit. Trying to remember here. But yeah, okay, so yeah, 0 to, all right. Well, as I said, this is pretty linear, but the way that it's set up, I'm not surprised. Obviously, we're going from 0 microamps where we're getting 0 volts, okay. And we get all the way to 100 microamps for like a fully lit room, and we are getting, let's see, getting, actually, yeah, we're getting about 1 volt there, so if this was attached to a light or something, then it would probably light up. And then we have Schottky diodes. You'll probably hear Schottky mentioned a lot. Schottky designation means it's just made from a metal semiconductor junction instead of the classic PN junction. Faster switching than even the fast recovery diodes. Very low forward voltage drop. Only about zero point 0.2 to zero point 0.4 compared to like zero point 0.7 for silicon diodes. So basically, it uses less voltage in its operation. It can't take as high of a reverse current though when compared to most diodes. Most current leakage, more current leakage than most diodes, especially when you get to high temperature. Reverse recovery is nearly zero, so this is faster than the fast diodes. 1N5817 to 22 models are commonly used by hobbyists. I think that's actually an entire family. Frequently used for DC to DC conversion, blocking diodes for solar panels, RF circuits. It seems like everything uses an RF circuit, and low voltage circuits. Now here I'm going to look at a Schottky diode, um, which is the one on the left here, or the right here, sorry. The one in 5817, and the other one is a standard general purpose rectifier diode. We got to put it going out the same pulses so that we can look at the recovery times. So let's look at the recovery times. D2 is obviously the regular general purpose rectifier, and D1 is the Schottky, which has very fast recovery times. Let's actually see if we can look at the numbers here. That, let's try that again. There, closer. Oh, white. I can't even see the numbers to get in that close. That's 5.02. I mean, it's really tiny. All right, we're changing things around just to look at the Schottky diode. Let's take a look at down at its forward and breakdown voltages. All right, I've taken it from negative 100 to 100. Let's look at those numbers. Well, the breakdown is going to be, oh, whoops, that's not what I meant to do. Breakdown is around negative 20 or so. Close enough anyway. All right, and then the real star of the show is over here. And that's where we start to turn on at only 100 millivolts, so zero point 0.1 compared to the zero point 0.3 or zero point 0.7 of other diodes. And then we have transient voltage diodes. These use the avalanche effect. Sometimes they're known as transient voltage suppression. It's a diode designed for sudden voltage spikes where it opens as an open circuit under most voltages, but it'll shut down suddenly when the voltage spikes over a threshold. It's meant to handle high surge currents with very fast response times measured in nanoseconds. And it either can handle multiple events, or it might be destroyed in a single event, thus just closing the circuit until it's replaced. It's used with USB and communication ports to protect against surges, surge protectors, power supply inputs, um, and it basically exists in microcontroller boards to protect them from power surges. P6KE 6.81 apparently is a common model, and it can handle up to power surges upwards of 600 watts as part of surge protection in a larger circuit. Now, for the transient voltage suppression diode, I'm going to go into LTspice. I had a little trouble trying to pull this off in QSpice. I might figure out later. But basically, yeah, we've got our EVS right over here. We got a specific model. Um, we've got our resistors, one for the in, I believe load. So, and we're going to be taking the voltage from negative 100 to 100. So we're just going to look at a standard curve. Actually, let me see if I can. So basically, unprotected would be this blue line right here if we did not have this diode. So this is about protecting against surges. It's in your surge protector. It's in a lot of other stuff, I believe USB as well. So basically you get a point right here where it just kind of clamps down the voltage in both directions. Let's see if I can actually, still learning my, see. Oh, there we go. Okay. Now let's see if I can actually bring up a, oh, there we go. I'm learning. I'm learning. Whoops, I want it actually on. That'll still give us an idea. Okay, place cursor on there. No, that's not what I want. Move cursor. Clear all cursors. There we go. So the bend is like right there. Let me redo this. Close that out. Good thing is this is not a separate window. So let's take a look. This is going to work. Oh, there we go. All right, so we can see where the breakdown is. You notice we're not getting that. This is something different than the traditional diode because, again, we're only using this for surge protection. But I think I don't know, 27, somewhere around there. I got to actually figure out these tools. See if this will actually give us our numbers. This is about, oh, 27 and a half. And same idea. So this protects against surges that go more than 27.5 voltages, either negative or positive, because it is a bidirectional TVS. So we come to light emitting diodes, and we've already talked a lot about them since they give us this, a very simple output on the circuit. All diodes emit some degree of light. It's infrared, so it's something that usually can't be seen by the naked eye. However, an LED decides to focus on efficiently generating light as its primary design. The threshold voltage is considerably higher than most other diodes, usually about 1.2 for reds, 3.3 for blues. A voltage below these numbers will fail to cause the LED to glow or to glow very dimly. Then there's Roy-Jubiv, which is the order of colors: red, orange, yellow, green, blue, indigo, violet. So the further you go from one end to another is going to affect what kind of voltage you need. They're very sensitive to current, so maybe 15 to 20 milliamps. You might be able to go a little higher. Higher currents than that will destroy the LED. Much less lower reverse breakdown voltage, hence they need to be very careful with reverse bias. Then we have laser diodes. Laser means light amplification by stimulation of emission of radiation. Instead of the light being scattered like you might have with an LED, it's focused by reflection between two small mirrors. The light is coherent, which means the waves travel in phases. It's monochromatic, a single color or wavelength, and highly directional. Laser diodes exist in I don't know, pretty much everything. You've got laser pointers, anything with optical discs, CDs, DVDs, Blu-rays, even barcode scanners. That's how they actually scan the barcode. Laser printers, fiber optics, medical equipment, all of these. A lot. There would be so many things that didn't exist without lasers. Laser pointers typically in the milliwatt range. So they're generally safe, but don't point them at anybody's eyeballs. Woodcutters and engravers are usually a few watts. They can do some actual damage to humans. And then we have tougher cutters, which are watts in the tens of watts, maybe even higher than that. Um, you might see basic laser pointers, laser diodes in some kits. Again, no real risk of laser burns, but definitely keep them out of people's eyes or a lot of other things. And don't go pointing them at airplanes. But keep in mind, lasers at any wattage can be dangerous, so be very, very careful. So just to wrap things up, there's many types of diodes and diode-like components that are closely related. I talked about diode versus triode, although triode might be only used with vacuum tubes, so some people will just call that family thyristors. Classic diode behavior isn't present in all diode types, or maybe just partially present. Specific models are extremely important for specific applications. They aren't always interchangeable. Look at voltage, current, power. Do your research on a data sheet. Simulators like EveryCircuit just kind of have a classic diode. Falstad lets you actually pick some models, and then if you really want to get fancy, you go with a Spice simulator. Uh, Xeno diodes and LEDs often, though, at least have their own components in most simulators. You might have to look to other simulators for different types. Well, that about wraps things up, so have a good one.